Hello and welcome to Computing Fundamentals 2. In this video we are going to discuss representing a graph and the graph's isomorphism. We often need to know whether it is possible to draw two graphs in the same way. That is, do the graphs have the same structure when we ignore the identities of their vertices? For instance, in chemistry, graphs are used to model chemical compounds. Different compounds can have the same formula but can differ in structure. Such compounds can be represented by graphs that cannot be drawn in the same way. The graphs representing previously known compounds can be used to determine whether a new compound has been studied before. So let us take a definition of isomorphism first. The symbol graphs G1 and G2 are isomorphic if there exists a one-to-one and onto function f from V1 to V2 with the property that A and B are adjacent in G1 if and only if function of A and function of B are adjacent in G2 for all A and B in V1. Such a function f is called an isomorphism. We will have more examples to understand this definition. Two symbol graphs that are not isomorphic are called non-isomorphic. In other words, when two symbol graphs are isomorphic, there is a one-to-one correspondence between vertices of the two graphs that preserve the adjacency relationship. Isomorphism of symbol graphs is an equivalence relation. So let us take an example. In this example, we have a graph G and a graph H displayed in figure 8, and we want to know if they are isomorphic. The function f with function f of u1 equal v1, the function of u2 equal v4, the function of u3 is equal to v3, and function of u4 is equal to v2. So there is an one-to-one correspondence between v and w. To see that, this correspondence preserves adjacency. Note that adjacent vertex in G are u1 and u2, u1 and u3, u2 and u4, and u3 and u4. And each of the pairs of the function f of u1 equal v1 and f of u2 equal v4, f of u1 equal v1 and f of u3 equal u3. So f of u2 equal v4 and f of u4 equal v2, and finally we have f of u3 equal v3 and f of u4 equal v2 consist of two adjacent vertices in H. It is often difficult to determine whether two symbol graphs are isomorphic. There are n factorial possible one-to-one correspondence between the vertex set of two symbol graphs with n vertices. Testing each such correspondence to see whether it is preserved adjacency and non-adjacency is impractical if n is at all large. So sometimes it is not hard to show that two graphs are not isomorphic. In particular, we can show that two graphs are not isomorphic if we can find a property only one of the two graphs has, but that is preserved by isomorphism. A property preserved by isomorphism of graphs is called a graph invariant. For instance, isomorphic symbol graphs must have the same number of vertices because there is one-to-one correspondence between the sets of vertex of the graphs. Isomorphic symbol graph also must have the same number of edges because the one-to-one correspondence between vertices establishes a one-to-one correspondence between edges. In addition, the degree of vertices in isomorphic symbol graphs must be the same. That is, a vertex v of degree d in G must correspond to a vertex of function of v of degree d in H, because a vertex w in G is adjacent to v if and only if the function of v and function of w are adjacent in H. So hopefully by this definition and example, we understand the concept of isomorphism of graphs. So let us take another example. We have a different set of graphs. We have graph G and H, and we want to show that the graphs displayed in figure 9 are not isomorphic. Both G and H have 5 vertices and 6 edges. However, H has a vertex of degree 1, namely E, whereas G has no vertices of degree 1. It follows that G and H are not isomorphic. Another example, we want to determine whether the graphs shown in figure 10 are isomorphic. So we have a graph again, G and H. The graphs G and H both have 8 vertices and 10 edges. They also both have 4 vertices of degree 2 and 4 of degree 3. Because these invariants all agree, it is still noticed that these graphs are isomorphic. However, G and H are not isomorphic. To see this, note that because degree of A equal 2 in G, I must correspond to either T, U, X or Y in H, because these are the vertices of degree 2 in H. However, each of these 4 vertices in H is adjacent to another vertex of degree 2 in H, which is not true for A in G. Another way to see that G and H are not isomorphic is note that the subgraph of G and H made up of vertices of degree 3 and the edge connecting them must be isomorphic. If these two graphs are isomorphic, however, these subgraphs shown in figure 11 are not isomorphic. Another example. Determine whether the graphs G and H displayed in figure 12 are isomorphic. Both G and H have 6 vertices and 7 edges. Both have 4 vertices of degree 2 and 2 vertices of degree 3. It is also easy to see that the subgraphs of G and H consist of all vertices of degree 2 and the edges connecting them are isomorphic. Because G and H agree with respect to these invariants, it is reasonable to try to find an isomorphic of the function f. We now will define a function f and then determine whether it is an isomorphism. Because degree of u1 equal 2 and because u1 is not adjacent to any other vertex of degree 2, the image of u1 must be either v4 or v6, the only vertices of degree 2 in H not adjacent to a vertex of degree 2. So we set function of u1 to be equal to v6. So if we find that this choice did not lead to isomorphism, we would then try, let's say, f of u1 to be equal to v4. Because u2 is adjacent to u1, the possible image of u2 are v3 and v5. And then we set v of u2 equal to v3, and we continue in this way using adjacency of vertices and degrees as guide. We set function of u3 to be v4, function of u4 to be v5, function f of u5 equal to v1, and function of u6 to be v2. We now have a one-to-one correspondence between the vertex set of G and the vertex set of H, namely function of u1 equal to v6, function of u2 equal to v3, function of u3 equal v4, function of u4 equal v5, and function of u5 equal v1, and function of u6 equal to v2. To see whether f preserves edges, we examine the adjacency matrix of G and the adjacency matrix of H with the rows and columns labeled by the images of the corresponding vertices in G. Those adjacency matrix of G and H are showing in the figure. So because A of G equal A of H, it follows that f preserve edges, and we conclude that f is an isomorphism, so G and H are isomorphic. Note that if it turned out not to be an isomorphism, we would not have established that G and H are not isomorphic, because another correspondence of the vertices in G and H may be an isomorphism. The best algorithm known for determining whether two graphs are isomorphic have exponential worst case time complexity. So, however, there are algorithms with linear average case time complexity. You can use public domain program to determine in less than a second whether two graphs with as many as 100 vertices are isomorphic. We will see those examples in the lab. Graph isomorphism is a problem of a special interest because it is one of a few NP problems not known to be either tractable or NP complete. The application of a graph isomorphism. The question whether graphs are isomorphic plays an important role in applications of graph theory. So, for example, electronic circuits are modeled as graphs in which the vertices represent components and the edges represent connections between them. Graph isomorphism is the basis for the verification that a particular layout of a circuit corresponds to the design original schema, determining whether a chip from one vendor includes the intellectual property of another vendor. In this video, we have covered and defined graph isomorphism. Thank you for watching this video and see you in the next one.